Right, so in this method of proof lessons, there are going to be 5 parts. First part, introduction, then we are going to do an example of direct proof, then we'll prove the contrapositive of a statement, then we'll do proof by contradiction, and finally we'll prove logical equivalences. The very first part, introduction, is it's important to realize that an integer is even if there exists k belonging to z such that some integer n, such as n is equal to 2k. Likewise, an integer as n is said to be odd if there exists k belonging to z, such as n is equal to 2k plus 1. And finally, an integer n is said to be divisible by another integer m belonging to z if there exists k belonging to z such that n is equal to mk. That's the introduction. Now, direct proof. Say, let's prove that if n is even, then n square is even. Okay, so if n even, then there exists k belonging to z such that n is equal to 2k. Well, so in that case, n square is equal to 2k square, which is equal to 4k square, which is divisible by 2. Therefore, n square is even. Now, same thing, let's prove that, I'm going to reuse this demonstration for proof by contradiction, so I just want to do them well. If n is odd, then n square is odd. Well, if n is odd, then there exists k belonging to z such that n is equal to 2k plus 1. In that case, n square is equal to 2k plus 1 square, which is 4k square plus 4k plus 1, which basically can be rewritten as 4 times k square plus k plus 1, where this part here is even, and then we add plus 1, so n square is odd. So we prove that if n is even, then n square is even, and if n is odd, then n square is odd. That's an example of direct proof. Now, let's move to proof by contraposition. So say we want to prove that if 5n plus 3 is odd, then n is even. Well, the contrapositive statement of above is if n is odd, then 5n plus 3 is even. Because you remember, I'm just going to change color, the contrapositive of P imply Q is not P, not Q, sorry, imply not P. Okay, so let's prove that. If n is odd, then there exists k belonging to Z such that n is equal to 2k plus 1. So in that case, 5n plus 3 is equal to 5 times 2k plus 1 plus 3, which is equal to 10k plus 5 plus 3 plus 8, which is basically 2 times 5k plus 4, and that is even. So, if n is odd, then 5n plus 3 is even. So we have proven the contrapositive of the original statement Therefore, the original statements must be true. Right. Proof by contradiction. Now, the traditional example is proving that root 2 is irrational. Now, to do that, we assume the opposite. So let's assume that there exists P and Q belonging to Z such that root 2 is equal to P over Q. So root 2 can be written as a fraction. And also that P over Q is a fraction in its simplest form. Basically, we don't want something like 4 over 8. That's not good. We want, we want 3 over 5. That's good. Yes, I mean, if it's not going to be 3 over 5, but a fraction that cannot be simplified anymore. Okay, so root 2 is equal to P over Q. Let's assume that. So that means that if we take the square of both sides, 2 is equal to P square over Q square. So that means that P square is equal to 2Q square. Oh well, so P square is even. Now you remember 2 pages before I've shown that if if P even, then P square even, and I also showed that if P odd, then P square odd. So here P square is even, so therefore P must be even. So if P must be even, so that means that there exists K belonging to Z such that P is equal to 2k. So, okay, so the equation 1 here, 1 becomes 2k square is equal to 2q square. So that means that 4k square is equal to 2q square. So that means that q square must be equal to 2k square. So therefore, which is even. So therefore, following the same reasoning than above, q must be even. Now that's a problem because p is even and q is even. So therefore, p over q, it's not a fraction in its simplest form, which contradicts the original statement. So therefore, root 2 cannot be written as a fraction. Okay, so we've done proof by contradiction. That's a typical proof. Now, finally, proving logical equivalence. Now, say, okay, let's prove that a 3-digit number is divisible by 3 if the sum of its digits is divisible by 3. Right. So, so let's say the number can be written as A, B, C. Right. So, okay. So the number would be 100 times A plus 10 times B plus C. If it's divisible by 3, then it can be written as 3k. And so, okay, well, what what I can do, maybe I can rewrite that as 99a plus 9b plus c, and then plus a plus b. Yes, and that's equal to 3k. So that means that a plus b plus c is equal to 3k minus 99a minus 9b, which, okay, we can factorize by 3, so that's k minus 33a minus 3b, and this is divisible by 3. So, okay, so what did we, therefore, so, okay, so what did we prove? We proved that if a number 3 digits number is divisible by 3, then a plus b plus c is divisible by 3. Right. Okay, very good. Now we need to prove the other way. which means that this way. Right, so if a plus b plus c, if a plus b plus c is divisible by 3, then there exists k belonging to z such that a plus b plus c is equal to 3k. So that means that, well, it's equivalent to, say, c is equal to 3k minus a minus b. So that means that the number n, which is 100a plus 10b plus c, can be written 100a plus 10b, and then plus 3k minus a minus b, which is 99a plus 9b plus 3k, and this is divisible by 3 because we can factorize by 3. So okay, so that we have proven so if a plus b plus c is divisible by 3, then n, which is 100a plus 10b plus c, is divisible by 3. So okay, so here we go. We've proven that way, and we've proven that way. So therefore, it's equivalent. Basically, the arrows go both ways, and we've proven that if a number, for a number of 3-digit numbers to be divisible by 3, then the sum of its digit must be divisible by 3, and vice versa. We've proved both ways, so the two statements are equivalent.